All right, welcome to this review of our Python length of stay prediction workbook. This is where you'll see some of the concepts from the class come to life. And I hope you're going to see that this is all handled through some pretty straightforward workflows that are enabled by key libraries that are built to do this for us in Python. And so in a practical way, this comes together, not easy, but it comes together in a pretty straightforward way. It's very understandable what we're trying to accomplish. So we start, as we usually do, by getting the libraries we need in place in order to operate going forward. After that, I've got the authorization to Google. You're going to be prompted to make sure you are logged into your Google account. After that, Colab is running the compute for free, so that's the good thing. But you need to choose this allow, use your account, continue, and continue. That is what's going to get you logged in so that you can query against our Health Analytics Lab project and that demo hospital system data set. Then we're going to run a query. And in this query, we are grabbing hospital encounter information, if it's relevant, ED, some patient information, and then we go even deeper. We look for orders, we do some aggregations of those, and build some features from that. We go ahead and get the number of orders, number of different types of orders, a couple different fields that could help us in understanding the patient. So here's the top of that data set so that you can see what it looks like. So that's just hitting BigQuery and returning the information. After that, we've got this cell here that's going to do a quick overview that's going to print out a summary of our data set and any missingness that we have in it. You can see there are missing ED chief complaints, ED to admit. There's no missing in any of the other categories. And that's because not every patient came in through the ED. So that makes some sense, but a good just checking step, because this is a piece of code you could take and use for your own data set and repurpose. This chunk, this function would be really useful to get that quick overview for you. Next, I want to start seeing the data. So we're going to be predicting length of stay. So let's just get to a distribution of that. That's a common step I like to take just to get it out in front of me to be able to see it. We are interested in splitting the numerical and categorical columns. So I will go ahead and look at each of these columns so I can see which is which, and I need to get them listed so that I later on can treat them differently. Numerical columns are all set to go, but the categorical columns, the predictive algorithms need turned into a number, and you're going to see how we do that later as we discussed in class, the different encoding options for that. Also grab a couple other things. We'll look at age distribution. Here we grab the ED to admit hours. We have a pretty even spread across that, but clearly doing pretty good. We get everybody in within 4 hours. Let's check and see something like, do we have some strange proportion between male and female in our data set? Doesn't seem to be the case. Also check and see if folks are coming in through clinic transfers or surgical. Top is the clinic. And this is just us getting data out and starting to see it a little bit better. From there, we could go ahead and do a similar look at the ED chief complaint. Why did they come here? What's the reason? And so we're seeing that many didn't come through the ED, and so those get all lumped into that grouping of none, and the rest have some common chief complaints that you would see coming in through the ED. I've got this helper function that doesn't come out as actually very necessary in this data set because we don't have large categorical columns where we have 100 or 200 ED chief complaints. But what you're going to see here is a function that would go ahead and find out if there is a count that is in there and that is rare. Then we would put it together into a group called other. So that's real basic treatment, right? So if there's just a bunch of random categories of ED chief complaint or whatever the category might be, that would put it into its own bucket of rare. That helps in modeling to make sure that you don't create a super wide data set. You'll see what I mean later. So it didn't find any that were overly rare to have to bucket like that, but yeah, let's move on. You're going to see why that matters when we get to the encoding part. So now we're getting to just a copy of the data set. That's what's going on here. And we're going to get the training and testing data sets set up. And so we're going to start by making sure we have those numeric and categorical columns properly set up. And I believe that we do. We also have this target here, length of stay. So we've got those variables to use when we split up our data. Because later we're going to say, here's what I need for training, here's what I need for testing. X is equal to those feature columns, or the numerical and categorical, and Y is the length of stay, the thing that we are predicting. And so then we just go ahead and see that information and pull out a distribution of our length of stay within our training set and make sure that the testing set looks similar. And now we're on to the handling of our categorical columns. And so we're going to do one-hot encoding, which is a really common approach. And especially if we have groupings that are not too many categories, as we saw is the case for us. And so by doing that processing, turning it into one-hot encoding, we get to a data set that looks like this. We go from a patient like this patient 651 who is marked as male and transferred and fall injury to a set of features that are all numeric, and you'll see by the column name how it is handling those categories. There's one column for each unique grouping in those categories. So there's one for patient gender female, one for patient gender male, and this patient is getting a 1 in patient gender male. So it continues that way through all of our categorical columns, and then some of our numerical columns are in there as well. So I guess this is just a showing of the categorical columns. We also still need that information mapped, so later on we can use it to evaluate how the algorithm is using these columns and be able to attribute it to just gender, not gender female, gender male, that sort of a thing. So here I am just pulling out some of that mapping so you can see how a patient that is marked in this way, which columns get marked as a 1. So this is just verifying that the treatment of these in one-hot encoding is happening as we expect, and I would say that it is. That the only thing returning as a 1 is patient gender male, hospital origin group transfer, and ED chief complaint fall injury, which represents this patient appropriately. So there we go. We've got data set up and it's mapping. And now we're moving on to model selection. So you're going to see that all we're doing is using a whole bunch of scikit-learn functions. So this is a library. Someone has built a whole bunch of code to make this kind of thing ready to go for you, easy to work with, because it's a common task people do in Python. Someone has built these great libraries of code that are sitting there ready for you to borrow. So you're going to see here, the couple of things we're doing is choosing what models we want to evaluate, and then we put them into a pipeline to test our data with each one of those models to see which one does the best. So of course there are people like data scientists that go and learn a lot of the intricate details of how these models operate, all the math behind them, to think through them. But in a practical sense, they are still doing this same step where they are evaluating just in an empirical way which one of these algorithms does the best against their task of prediction. And so the real evaluation is about whether or not you need explainability in your data set. That sends you towards some models, like actually the ones here, are all useful for explainability, except gradient boosting has some issues with that. And then after that, we are evaluating how the algorithms perform given the unique set of performance criteria we have for the problem. So we're going to start in a really basic way to say check every model, get a basic observation of their mean absolute error in days. So how many days off are they on average when predicting length of stay? And you'll see that listing here. And so lower is better in this situation. And so the ridge regression and linear regression, or simpler models, actually did better in this initial pass of the data. So this is just getting to a starting point of what are we going to consider as the models. And we move on. We keep moving down to do an actual training pipeline. Actually, I'm sorry, what we're going to do here is extract some of the features and figure out what the models are zeroing in on. So I'm going to rerun this because I don't think I actually had run it in this go. And then it's going to extract the features from our best model. And depending on the best model, you have to do that slightly different. Since our best model was that ridge regression, it's going to use this part of the logic. If the best name is ridge, then it's going to do these things. It's going to pull out these coefficients in order for us to see what is having the largest impact on adjusting our length of stay. And so you're seeing an ED chief complaint of fall injury. So if someone has a 1 marked in that category, they are seeing the most impact on the length of stay. So very interesting, it's a negative length of stay if they have that. This is an absolute coefficient, I'm sorry, so just making those all positive. So the biggest impact is coming from ED chief complaint, which would reduce length of stay if it's a fall injury or cough, but if their ED chief complaint is fever, that actually increases their length of stay relative to the average. So this is helping see the importance of the different features that are in the data set. How is the model making its decision? So this is to the point of interpretability. If you were to go to really complex types of models, you actually can't extract this sort of understanding about how the model is working. So that's the benefit when I'm talking about explainability. This is what it boils down to. Can you say what the model is using to make its decision? And we can say this is sort of the weighting, in a sense, of how the model is making its decision. Okay, so we bring that out into just a graphical format so we can see sort of proportion of that importance. And then just as an example, we predict a few cases. Here for patient 425, we predict 4.44. So we're just making sure that the piping is working and we can take new information, not know their length of stay, and predict what it will be. All right, after that, we move on to the task of hyperparameter tuning. So this is the process of setting the variables that you can adjust in these algorithms. And so the main thing that we're going to be doing is here in this cell where we are going to set out for the options we can set in these different models. We're just going to do a random forest because it's useful because you can see there are multiple things that you can set. And then this ridge regression, which just has the one thing. We're going to set up ranges of those variables. We want to test what's our different accuracy when we set these n estimators to one of these 3 values or max depth to one of these 3 values. And so we go ahead and run the pipeline again, but with these different combinations of settings. And we result at something just like this. We're running a random forest and the ridge across those options to see when we set the max depth to 6, the minimum leaf samples leaf to 5, and n estimators to 400. Here's our mean absolute error. And then the continued performance for all these other settings. So this is starting to give us a sense of what is the right setting for these. And we're tuning to try to get very good performance. But there's a second step to this. So this is going to help us look for what are the right ways to set those variables. Presumably you might just choose something like the minimum, mean absolute error. And I'm just going to point out, because you'll see later an example where we change this, the max depth here is set to 6. Just keep that in the back of your mind. Then we go to the ridge. There's less things to change, but here's the performance as you change the alpha there. And so let's go ahead and look at that sort of visually. Oh, sorry, I didn't run this on its own. Keep forgetting because it has some of the stuff there. So now it's running and doing that work. It has to predict, given one set of variables, predict again, predict again, predict again. So it can take a little bit to get through all of those different permutations of the prediction, but here it comes. After it finishes the random forest, should have a quicker job of running that ridge regression. And we're going to get to the same result, a table of, given these settings for the model inputs or model variables. Here's the result. Okay, so now the workbook, this instance has that information, and I can move on to this next step, which is looking at that random forest model. If we were to change the n estimators from 100 to 200 to 400, what happens with our performance? It gets better as you add those more n estimators, or basically add complexity. So, okay, one intuition we have is to add complexity, and we saw above that there's some good performance with a little bit higher max depth, but not the maximum, and the leaf's also at one of the higher ranges. So just keep those things in mind. Next, with the ridge, we see the performance at different settings of that alpha. So alpha, higher performance. The lower mean absolute error is there in the visual. So now we think, though, about overfitting, because when we do that initial performance review and we're tuning, we are working on training data. But we actually don't just want it to train. We want it to test and see how it does if we were to let it see new data. So we've got a simple example here where we've gone ahead and we are going to set the model for a random forest. We are going to set the n estimators to 200, and then we are going to see what is the performance if we were to have the max depth be 2, 4, 6, 8, 12, or none. I'm going to get rid of none because it's kind of distracting here, honestly. I'm going to rerun. And now we're going to see what this comes out to. Nice. Okay, so now we've got a graph that's going to show us how did it perform when we set the max depth to these different levels. So we set the max depth to 2, 4, 6, 8, and 12, added complexity basically, and guess what? Our training kept getting more and more performative. Great, so it can learn the training data really well. But look what happens when we do a cross-validation and we go and test it. Once you test it, you actually get worse performance as you add that depth. That's because that extra complexity is learning some nuance about the training data that doesn't generalize to the overall data. So when it sees new data, it does worse. So this actually tells us, hey, we actually probably need to restrict the max depth. And so that's what I do next, and show you an example of the performance in a random forest if we just do 200 trees, which is, kind of standard across these two, but to not limit the max depth. It can take whatever depth it wants to, and we get an error of 1.57 days. But if you restrict it and say, no, you can only go to a max depth in this random forest model of 2, so you can't go as complex, you actually get a better performance when you go out to new data. So that is the basic workflow of getting a prediction task done in Python. So I hope you enjoyed that. Thanks for sticking with me, and we'll keep moving through turning this into a full pipeline for evaluation across another prediction task in the next video.